Good morning to all of you. We're very excited to be here and to present to you SIRONA, which will be the first French satellite to orbit around the moon. So, who are we? For one part, we're 15 engineering students from the engineering school CentraleSupélec. CentraleSupélec has many labs and decades of experience in the spatial field. And this year, the Space Center of CentraleSupélec was launched, and putting all this knowledge into one federating project. Through the year, as students, we work tirelessly on this project with three main goals, which were to learn by experience, to have a real scientific impact by providing new data on the moon's environment, and to be part of the engineering process of such a project. So what is SIRONA? SIRONA takes its name from the Gaulish goddess of the lunar light. It will be, as I said, the first French satellite to orbit around the moon. 12-unit CubeSat, around 20 kilograms. First launched in low Earth orbit. Then it will travel to the moon with electric propulsion, and then orbit the moon. And there will be a various amount of scientific experiments. And now let Rémy explain to you more in detail what those experiments are.
Exactly, thanks. So a few words about the different scientific objectives and the scientific specification of the mission. First of all, the first scientific payload is Asterix. It's a deployable telescope which will count the number of craters at the surface of the different lunar seas. And we know that this will give some interesting information about the solar system, and its formation. Really interesting information about these ones. So, for example, we'll be able, by this process, to test the cataclysm hypothesis by providing the higher resolution images. A few words about the deployable aspect of the telescope. So, on the left, you have the deployment of the first stage and the final deploy configuration. What you need to know, and it's important to mention it, is that the whole telescope will occupy less than a half unit of the CubeSat, and then once deployed, it will be like 33 centimeters long. On the right, you have the different elements, the key elements we've developed internally about the deployment of the telescope. So there are the torsion springs, the stops, and the release mechanism, and all these different elements enabled us to be able to deploy the telescope once in lunar orbit. So the next slide is really important to clearly understand the added value of the Asterix on board SIRONA. On the right, you have the kind of image you can get with the probe LRO, so Lunar Reconnaissance Orbiter, which provides us with the best images in terms of quality of the lunar surface. Then in the middle to the scale, you also have the kind of image you can get with the Asterix, we intend to get with Asterix, and on the left, you have the kind of image you can get with a telescope the size of SIRONA, but not deployable in another CubeSat mission, for example. So why would we develop SIRONA and why would we develop Asterix on board SIRONA when we have LRO? 2 points are important here. The first one is that some of the images provided by LRO were not performed in the best enlightenment conditions for counting the different number of craters. So that's why we need Asterix. And the second point is that LRO has not covered the whole lunar surface. So that's also another answer to this question. That's why we need to develop Asterix on board SIRONA. The second scientific payload on board SIRONA is the biological experiment named Obelix. So you may know that the international agency are moving towards the lunar orbit, the lunar environment. But there is a key issue that needs to be addressed. It's the impact of the different cosmic rays in this new environment on the different living organisms, especially, for example, if we want to have cislunar stations in the future, or even colonies in a further future. So here you have different images about the deployment of Obelix. So why is it important? Because the longest stay of the living organisms in the lunar environment is the Apollo mission with nearly a week. So it's six days and 11 hours. So this is not enough to fully understand the whole phenomenon. That's why we want to develop Obelix. You have a design of the different wells, the wells in which different living organisms will develop in several developing conditions. They will evolve, and we'll be also able to evaluate and to assess the performance of different shielding materials, and this kind of information would be really relevant if you want to develop modules in the futures, for example, for the CNRS stations. So now let Romain talk about the mission analysis aspect.
Thank you. So to go from the Earth to the Moon, SIRONA will follow a big plan trajectory. This trajectory was selected with various parameters, the main ones being to reduce as much as possible the exposure to the Van Allen belts to protect our biological samples and the onboard computer to the cosmic rays, which could damage them. Then to minimize the impulse needed to go from the Earth to the Moon, and underlying that is the propellant mass inside the SIRONA. And finally, for the traveling time period from the Earth to the Moon to be under 6 months, as to maximize the working period in the lunar orbits. So what does SIRONA look like? And here see the 12-unit CubeSat with deployable solar panels on the side and deployable patch antennas on the side too, where will be placed the main thrusters as well as the tune cans. And to see a more in-depth description of the subsystems and the way they interact with each other, you can here see the electrical power system with mainly the batteries and the solar panels used to charge them, the command and data handling, which will be the brain of our satellites, communication with mainly uplink and downlink with S-band and X-band patch antennas, thermal control, as well there are critical subsystems we need to control temperature, such as the samples or the battery we wouldn't want to freeze. The propulsion system with, as I said, the main thrusters, which will be electric, and as well as pulsed plasma thrusters, which will be used for attitude control. Then the payload, as described by Rémy, mainly aesthetics and optics, but not only. The attitude and determination control system with mainly the reaction wheels to control the attitude. So if we put all of those systems together, you can here see that the main part of our satellite is still empty. And that is one of the goals, one of the objectives of SIRONA, is to leave 7 units so far for potential payloads, future payload. The goal is to be a bus for a new scientific experiment in the lunar orbit at a low cost. And I'll let Rémy detail more of the systems.
So a few words about the different aspects and subsystems of the mission. First of all, the structure. So on the left you have the different cells arrangements in the primary structure, and on the right the different strain simulations that were performed on the structure. We developed a new type of structure limiting the mass and the volume of our 12-unit CubeSats, but providing a cold shielding for the different subsystems and the different electronics inside SIRONA. I have to mention that unlike different terrestrial CubeSats, we're in a lunar environment, and the cosmic rays are just for a harsh environment. We need to think things differently and to be able to protect our subsystems, not like in terrestrial orbit where we have the magnetic field helping. So this is not the case here. Another aspect is we developed internally is the plasma thrusters. So it will be used in the attitude determination control system. In fact, we need to rotate the satellite in the different phases of our mission, whether it is about communications, about science, or about propulsion. So this purpose will be achieved with reaction wheels. But the thing is, these reaction wheels will saturate. They will reach a threshold in terms of angular velocity, and we'll need to desaturate them in order to use them in the different following phases of the mission. That's why we want to use an independent system called PPT, pulse plasma thrusters, just to achieve this goal, desaturating the different reaction wheels we need. On the left you have the proof of concept and the product we developed internally in the Space Center. So with the different elements, we use solid propellant for the different advantages they provide in terms of integration, simplicity, but also we don't have any problem with the different problems we could have with gas or liquids. And on the right you have the final design concept that we intend to implement in the final configuration of SIRONA, with the tuna cans, and in each tuna cans will have 3 thrusters, 3 PBTs, and the goal is just to put in common the different electronics for different PBTs in order to gain mass and volume, and also to have a compact system, and that's the real added value of the system.
So, as you may have seen, one of the particularities of our mission is the amount of power it will need. And that will be achieved by deployable solar panels. Those panels will be 3 times the size of SIRONA on each side. And well, this will achieve close to 100 watts of generated power through those solar panels. In order to maximize that power, we'll add an extra degree of freedom to those panels by adding a rotation around their axis. This will be achieved by the PADA, so the panel array drive assembly. On the mechanical design, one axis rotates in the opposite side to the solar panels in order to negate the general torque of the satellite. So if we control the attitude of the solar panel, there will be no perturbation to the satellite. Another note is that the selected position of the solar panel with the PADA was used in order to minimize the impact of the torque due to the radiation pressure. The same subsystem will be used for the antenna, the deployable patch antennas. Those antennas would be S-band for low power budgets for uplink, and for downlink with X-band for medium power and a high data rate, as the scientific data which will be produced will be quite a high amount of bytes.
So we now end this presentation with the mass budget, giving an overview and summarizing the whole mission. So I will not detail the different elements in terms of mass. This is a conservative mass budget of the whole mission. What is interesting is the bottom line, as usual. Here it just states that we have approximately 8 kilograms free and avoidable for the different payloads. So validating our idea for SIRONA to be a real space bus for the scientific communities, and eventually establishing new partnerships with different institutions and organizations all over the world with the scientific community. As you have seen with Obelix and Asterix, they are really relevant in terms of the actual context, the current context. I mean, we need to go, this is the moment to develop such an instrument to learn more about the lunar environment and the lunar orbit. So thank you very much for your attention. I just mentioned here that we have 5 posters presented in this conference about the different subsystems, so namely the telescope, the biological experiment, the PBTs, and also 2 others about the mission. So thank you very much.
Thank you very much. Any questions? Okay, lots of questions. Start from there.
2 questions actually. One with the orbital mechanics. You go in orbit over the polars. Isn't that a huge amount of data being used for getting to the plane of the moon? First, and the second, what is the main propulsion system?
Well, on the trajectory, the subject is currently under investigation. We have we'll use the GMAP software in order to determine that. So on that question, we'll produce more data and share it with you later. On the propulsion system, well, it's directly correlated to your previous question. So far, there was a various amounts of process system. Well, maybe a Hall effect or ionic, but so far I cannot disclose what we showed on that.
Thank you.
Thank you very much. Just a similar question to the previous one. So about the data velocity budget, do you have an, for example, in which orbit the CubeSat is released, the LEO orbit or in G orbit?
Maybe I can answer to that. So we're going to have delta V budgets to reach the moon below 1 kilometer per second.
1 kilometer.
1 kilometer per second maximum, and we're going to be released mostly probably by PSLV in polar orbit. and we're gonna reach 200 kilometers altitude orbit around the moon.
And another question. So you said in the mass budget that the main propulsion system is about 5 kilograms. Does that include the propellant?
Yes.
And based on like a specific impulse of, can you give me a range of specific impulse? 3,000 seconds. Thank you.
I noticed there was a magnetometer under your payload. Is that for was the magnetometer for attitude determination, or was it for science?
No, exactly. It's for attitude determination, but we'll use it only around the Earth orbit. And once right in the lunar orbit, there we can't use it because there's no real interesting magnetic field around the moon. So here we use the PBTs to desaturate the action loss.
Well, there are some very interesting magnetic fields around the moon, but it's probably far too small for.
That's it.
Yeah, okay.
That's it. When I say not interesting, it's not interesting for the attitude determination. Sorry. Yeah.
Okay, I'm sorry.
There will be several days for the saturation.
Yeah, one question on that.
Can you tell us a little bit about how you are going to analyze the biological sample in the lunar orbit?
Just a minute.
We have also poster on that. We have a poster dedicated to the biological.
You mean on the type of methods we use turbidimetry? So to assess the evolution of the different living organisms in the different wells. So typically we just put some lights and we just measure the residual that we get once it has crossed the different samples. So that's it for the for the type of method. So the law behind that is it's not the bare lumber law, but it's similar law. So that's the kind of thing we wanted to do.
One last question from that?
Thank you for your presentation. As far as I understand, you have many things under development now. So, when do you expect to be launched?
The Space Center was launched this year, and the objective is to launch SIRONA in 4 years. But there are other projects under investigation, not only SIRONA.
Okay. Well, thank you very much.